Okey. So dah record ni. Okey, saya kemudian nak share screen. Okey. So kalau dah share screen ni, maksudnya saya dah tak nampak lagi lah chat tu Susah sikit nak nampak Webex chat tu. Okey, kemudian minimize. Okey. So kita mula dua suku lah Kita harap yang lain tu masuk lah Sekejap Okey, silent the handphone. Okey, including my own phone silent. Atau mute Okey. So yang ni betulkan saya dah minta itu betulkan. Yang ni lah quantization delta V. Inilah quantization step. So nama lain dia juga kita kadang-kadang kita panggil quantization interval. Okay. So benda yang sama dia ada banyak nama. So delta V lah. Okay. So error ni kita dapat tolerate kalau delta V over 2. Okay. So kita tunggu dulu yang another 2 minit Yang ni just kebetulan saya tengok yang 7 bits. Maksudnya X, 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 X lah. Contoh 01, 00, 101. So ada 7 bit ke semuanya lah. Okay, so another 1 minit lagi Dapat pun lama. Hari ni kita selesaikan slide Slide week 3 kita kena habiskan. Dan kita akan review past test lah. Jadi, okay. So, dah 2 suku Jadi, saya mula terus. Okay, Assalamualaikum. So, kita akan continue kepada slide week 3. Okay, yang ini saya lepas saya bagi sebagai homework So, harap masing-masing dah cuba. Okay. Dapat tak post-it 13.262 tu dapat tak bersamaan dengan yang ni? Okay. So, jika tak dapat, boleh approach saya masa kelas fizikal kelak lah. Okay. So, kita terus kepada yang next slide seterusnya. Okay. So, non-uniform quantization ni juga telah didiscuss lah sebelum ni, tapi tak berapa detail So, non-uniform quantization ni actually mudah saja. Konsep dia ialah kita punya delta V tu, quantization error tu, quantization interval tu, contoh inilah delta V1. Contoh saja. Kemudian kita ada satu jarak lagi kita panggil delta V2. Contoh. Kemudian kita ada delta V3. Nampak tak? Dia semakin rapat. Okay. Maksudnya, dekat sini kita boleh nampak delta V1 tak sama dengan delta V2 tak sama dengan delta V3. Contoh. So, bila ada range of V peak to peak, contoh 5 volt ke negatif 5 volt, tetapi jarak untuk delta V adalah tidak sekata atau tidak sama lebar, so itulah yang dipanggil sebagai non-uniform quantization. Okay, so apa yang berlaku ialah kenapa masih dilakukan, kenapa why we actually do this non-uniform quantizations. Okay, so non-uniform quantization is maybe not cover much in your syllabus, but it is covered just quite surface lah. So for example, the non-uniform quantization, for example, if you have signal, for example, signal ni contoh supaya you faham, so that you understand the concept. Let's say you have 5 volt, and then let's say you have a negative 5 volt, and then you have a signals. Let's say a signals very low, very low. Okay, like this. Okay, so what is that? What we do is that with non-uniform quantization, we will have a smaller step for lower amplitude and larger for higher amplitude. So ini supaya macam mana? Supaya we can capture as much as possible the variation that is exists only on the lower amplitude. Because larger amplitude mungkin tak ada atau kurang. Okay, contoh macam ni. Let's say we follow logic. For example, this one is 2.5. Follow logic first, 2.5. So if we are following uniform quantization, let's say we want to quantize 4 level. So it will be like this, right? 4 level up and 4 level below. So it will be equivalent to 8 level. Okay, 8 level quantization, which is L equals to 2, 3 equals to 8. Okay, so 8 quantization level with the bit, let's say the bit is 3 bits. So if we are using uniform quantization, okay, if you use uniform quantization, so the signals, the variation to capture accurately this discrete level may not match because we only have option of this or option of this level. Okay, while at the same time we know that there is no amplitudes or no information above that. So membazir lah, macam membazir. Okay, jadi what uniform non-uniform quantization does, okay, for example 3 level ni, for example, so the what non-uniform quantization done, okay, so kita buatlah sini 3 instead of 2 kan, kita buat dia sampai 3. Dekat sini dia tu macam ni, so kita nampak this one is more lebar, delta V1. Let's say this one we call it delta V2, delta V3, yang this one, and then we have another delta V4. Okay, so for this one, this when we do non-uniform quantization, we able to capture or we able to quantize the lower amplitude for signal that having lower amplitude. Okay, so ini antara kelebihan lah. So when we do non-uniform quantization, maksud signal tu kita lebih dapat capture, right, pattern. So in terms of logic, signal to noise ratio, signal kita meningkat, kita dapat cari quantize lebih. So that's why indirectly it will improve our SNR. Okay, so implement using mu law and A law. This one is in the previous communication principle akan belajar lah. Mu law dengan A law. However, for biomedical communication, we don't study lah, but you can study as the slide has been shown to you for the other courses if you want to learn more. Okay. Next is actually data modulation. Data modulation is actually not that deep. We not cover not deep, and then is just for your information, and the information is quite even more surface. Okay, so data modulation is they are using 1 bit. Okay, they are using 1 bit to represent the informations. Okay, So I will show to you using our using other course SEEU 3533. Okay, that one I will show. So simple but suffer slope overload and granular noise. Okay, so let's I unshare the screen. Okay, and then we go for the data modulation just for you to know. Okay, pulse modulation. Okay, so I share again the screen. Okay, where? Okay, share again the screen. Okay, okay. So now, this is data modulation signals. Okay, data modulation signal. So what happened is that it's only using one bit. Okay, and then is of course because one bit is either zero or either one lah. So we're not going to have 00, 01, 10, 11. We're not going to have that. So it's actually quite simple for the implementation of the data modulation. If if the current sample, okay, you see here, if the current sample is smaller than previous one, so this one is current sample, for smaller than previous one, then we would have been having zero. Okay, so now um we go for the most obvious one. Okay, this one. They say that this is the current sample and this is the previous sample. If the previous sample is bigger than the previous one, so it would be 1. Okay, so and so on. So however, this one is will suffer a problem of we call is a steep noise like this, because at certain point in time, uh, it will be diverged. Okay, so this is one of the disadvantage of this method. Okay, so we call it a slope overload noise. Okay, so however, this one is to overcome this is the steps. Okay, not covered in your syllabus, but you can read. Okay, this one has been shared previously. Okay, now we continue for our next slides. Okay, wait for one. I need to see some message. Okay, so in show. Okay, so we continue. So this is enough for your syllabus. Okay. So additive, then to solve the problems that we have in the delta modulation, so we have adaptive modulations. So what adaptive modulation is that we will change or we will vary our step size. Okay, so it will reduce the slope overload noise, and this is widely used in biomedical voice compression. Okay, so this one is just for you good to know and for you to memorize lah. Okay, we don't involve any equation for delta modulation and adaptive lah. Okay, delta modulations. So the next is actually on the line coding. Okay, so line coding. Okay, so we go for the we again I ensure and then we try to see in the other slide courses more detail of line coding. Okay, wait for a while, just so that you can see it. Okay, share the screen again. Okay, so this is the slide on the slide 5. Okay, chapter 5, radio digital modulations. Okay, so what is where does line coding occurs? Okay, so before previously we have learned, okay, from the previous slide. So we have learned on the analog. This one we have learned amplitude modulation, frequency modulations, and then after that, the signal that we have here is still analog. Okay, the signal that we have here is still analog. Then if we go through this analog to digital converter, macam microphone you lah. Okay, so it will undergo the process sampling, quantization, and also coding. Okay, so this one, all of that you have learned already, SQC. Okay, so this coding just now is in the previous slides I gave as a homework. Okay, so you try first. If we have problem, we can meet in the next class. It's easier to explain during face to face. Okay, so next, after we complete the process, we complete the process of SQC. Okay, anyway, before I forget, if anything, just interrupt me because it's not easy to see the WebEx chat. So then here, line coding. So line coding, you will be introduced to this one is we call it return zero. Okay, and then you have none return to zero. This one we call is a alternate mark inversion. Okay, this one is ASK, FSK, PSK is the same concept that you understand of the amplitude modulation, frequency modulation, phase modulations. So PSK we call it a phase analogy. They are the same. Okay, phase shifting. This one is amplitude shifting. Then we have FSK, which is frequency shifting. Okay, so let us go to different slides. Okay, this one is just so that you can know. Okay, okay. So if you see this slide, okay, we have line coding examples. Okay, we have Manchester coding. So this one, For this one, maybe I will photostat, or maybe I will scan it. Either I photostat or scan the pages from the module, so that you know all of them. Okay. Uh, so this one is just a summary. Okay. Manchester coding, alternate mark inversion. Okay. So this one is used in alternate and medical data link. Okay. So let's us go on to the previous slides. Okay. Okay. So this is the amplitude shift keying. Okay. Um, for now, maybe we didn't cover yet. We need to go to this AMI and RZ. Perhaps it's in the previous slide, in the other slide. Wait for a while. Okay, this is chapter 4. Okay, so wait, let's see. If it's not there, don't worry. Okay, it's here. If it's the detailed one in the module, I will share it. Okay, remind me if I forget. Remind me to share all of this, RZ and so on, to you. Okay, so let us see few examples. Okay, so that you understand the concept. Okay, what does it mean by it? Okay, so this one we call it is unipolar, unipolar non-written to zero. So what does it mean by unipolar? Means it's only have one polarity. So if it's bipolar, bipolar, so you will going to have a positive volt and negative volt. Let's say this one is 0 until 5 volt. Okay, perhaps this one is maybe 2.5 positive until negative 2.5. Okay, so this means by bipolar and unipolar. And then we have here is non-return to zero, means every complete cycle, or every complete cycle, there is no transition to zero in the middle. Okay, again, non-return zero means the waveform does not return to zero in the middle of the transition bit. Okay, the bit here, right? Okay, if we transit maybe to the next, before the next bit, but in the middle we don't have non-return to zero. So we have return to zero. So what does it mean by return zero? In the half cycle of the one complete bit, it must return to zero. Okay, then up again and go down again. So this one is zero, but zero is still zero, right? But the next return to zero in the next second half, so still zero. Okay, so this is what it meant by return zero or non-return zero. So it's quite easy, right? Straightforward. So this one is B, bipolar. So you have positive and you have negative. Okay, so this is the bandwidth. Okay, the bandwidth that you know remember the concept, right? The concept, for example, period. Period take to complete one cycle. Okay, let's say this period. Okay, now we have this period, right? Become longer, right? Compared to this, because here, okay, because here it it takes half of the period to complete. This one is take one period to complete. So the bandwidth, or 1 over t, is become bigger, right? Is double. It need double, which is t, in order for it to finish. So 1 over the period, which is very longer. So uh, that's why you have FB over 2, means twice longer. Then you have a bandwidth FB here. Okay, if you see here, it takes half of the period to complete. So what does it mean? The frequency is actually twice. Okay, so FB times 2 divided by 2 for the slower one. So for the faster one, because of it takes shorter time to complete one cycle, so times by 2. Okay, so that's why you have FB. Okay, so this one is straightforward. This one is also one cycle. This one is it have one cycle here. Okay, so that is the reason. Now, we go for this bipolar, return to zero. Bipolar, it must return to zero. Okay, so what does it mean by alternate mark inversion? Okay, alternate mark inversion means the next bit uh will be flipped. Okay, so what does it mean by alternate mark evasion? The next bit will become flip. Okay, so wait for a while. Wait for a while. I just scan the page. Take the photo for you to see. Okay. Find the page. Wait for a while. I'm going to take photo so that you can refer to them. So you don't have to buy this module, because this module is for others courses. Okay. So since this is a new course, the syllabus is not identical, but some of them is we can still take from the older course. Okay. So I say to our Telegram. Okay, so it has been shared. It has been shared. If you have problem in understanding it, feel free to let me know. Okay. 192, 192, 192, 132, 134, 133. So I miss 131. Okay, so it has been shared to you. Okay, next, we don't waste so much time on this. Okay, let me please stop sharing the screen. Okay, so we continue with our on slide. Okay, for example, sini slide. Sekejap Kenapa cursor saya tak keluar Oh, battery, mouse, yang ada apa? Tapi mana cursor dia? Oh, ni. Okay, okay, okay. Thank you, thank you. Hilang pasal. Sekejap, sorry, sorry, Kenapa dia macam ni? Oh, ni tak apa. Kejap, Halo, macam mana ni? Sekejap. Ha? Record. Kejap, There's a problem with the display. Oh, ni dah berlaku dalam kelas sebelumnya. Apa tak rasa tu? Macam mana ni? Ha? Sama je. Kejap, apa yang berlaku kat hmm. Pakai track code sama juga. Okay. Kena restart network. Semalam hari tu saya berlaku juga ni, saya kena restart. Okay, so kita rehat dulu Laptop saya hang ni, tak tahu kenapa. Dia punya cursor ni. Okay, so we continue at 250, okay? Okay, kita start. Boleh pula yang ni, Fazal. Boleh pula. Pelik-pelik je.